Good afternoon, all of you. Today we will look into our seventh experiment, K nearest neighbor algorithm. We have already seen uh, simple linear regression, how linear regression works and its performance analysis. For this experiment, we will learn about the K nearest neighbor algorithm or KNN algorithm. Uh, Before going into the KNN algorithm, we know that machine learning algorithms are classified into supervised, unsupervised, and reinforcement algorithm, in which supervised algorithm deals with labeled data, unsupervised algorithm deals with the unlabeled data, and this reinforcement algorithm deals with the reward and penalty way method of learning. And in the labeled data, for numerical data, we have regression, and for classification, when will we go for classification? For categorical type of data, in which logistic regression also comes under classification, because we have seen that logistic regression will give yes or no values as an output. And today we are going to look into the KNN algorithm. So KNN algorithm is a supervised learning algorithm because it is learning from the labeled set of training data. And supervised algorithms can be classified into regression and classification, where regression, the target attribute will be a numerical value, and we such as to predict whether the weather level or the number of items sold, etc. For classification, the target attribute will be categorical, and this helps us to classify whether the given object is a fruit or a vegetable, cat or a dog, etc. So what is this K-nearest neighbor algorithm? K-nearest neighbor algorithm is a supervised machine learning algorithm used for classification and few regression tasks too. Okay. So what is K-nearest neighbor? K-nearest neighbor is a very simple and easy to implement supervised machine learning algorithm. It can be used both for classification as well as regression, but mostly for classification. It is a lazy learning algorithm. What does it mean by lazy learning algorithm? It does not learn during the training phase, but instead it just memorizes the training data set as such. And it does not make any assumptions about the data because it's not at all doing any kind of learning. So no non-parametric learning algorithm. It's a non-parametric learning algorithm. And how is this K nearest neighbor algorithm working? It classifies the unlabeled object into the target class depending on the similarity features of its neighboring object. For example, here, if you could see, there are two classes. One is blue class and the other one is yellow class. And in blue class, we make the label, or we term it as, it is labeled as class A, and for the yellow class, we are labeling it as class B. And now a new object comes. What is this new object? This new object, now we have to make sure whether this is coming under class A or it is going to be classified under class B. So what is that we have to do? We have to find the distance between the unlabeled data with all the labeled data. So this is the star is my unlabeled data, and the class A and class B data points are all labeled data for me. I'll have to find the distances from the unlabeled data to all the labeled data points. And this K, in KNN, the K denotes how many neighbors we have to consider. So here, when K is equal to 3, we have to consider 3 neighbors. So after finding out the distance, we have to categorize the data points based on ascending order. So out of which these 3 neighbors are the nearest neighbor for the unlabeled data. This unlabeled data has, as K equal to 3, we have to take only 3 neighbors. So we consider the 3 neighbors which are very close. The distance are very near to this. This unlabeled data should be very near to any 3 of the data points. So we have found out that these 3 data points are very near to the unlabeled data point asterisk. So the star. And now, out of which we are finding out the class or the labels these 3 data sets belong to, in which these 2 data points belong to class B and this data point belong to class A. So now we can assume or we can classify the unlabeled data asterisk belongs to the class B because of the majority number of data points available in class B. The same way, when k equal to 6, we have to take six neighbors who are near to this unlabeled data point, out of which we have four data point labeled data which are of class A and two data point which are of class B. So majority is class B. So we assume that this unlabeled data belongs to class A, the blue color. This is how the algorithm work. And to find the distance between the two data point, we can use the distance measures like Euclidean, Manhattan, Minkowski, and there are so many other distance variables, distance formulas that are available. And we use Euclidean distance because it does the measure perfectly well considering all the features. So Euclidean distance is the direct or the least possible distance between A and B. So this is the formula, root of x2 minus x1 the whole square plus y2 minus y1 the whole square. When we take the Manhattan distance measures along the axis of the right angle. So we'll take the absolute value. If you take Manhattan, it takes the absolute value. But when we take the Euclidean distance, it takes the square root of the distance value. So either of this formula we can use. So we'll be using Euclidean distance. So how is this algorithm going to work? We'll have to load the data, initialize k. So initializing k value is very important because when we see in here, when k equal to 3, this unlabeled data belongs to class B. When we increase the k size, it becomes class A. So one data cannot be both class and class B because of varying k. There is no fast and hard rule to implement or to find or to analyze our k. K can be calculated by a thumb rule, where k is less than square root of n, where n is the number of examples. When my k is too small, then it is very sensitive to the noise points, and when it is too large also, it works well, but it may include majority points from other classes as the input. So we have to make sure that selecting k or choosing an optimal k value is very important. That can be done based on the repeated number of execution of the algorithm with the training and testing data sets to make sure that k is correctly classifying the object, the unlabeled object. So now this is the KNN algorithm. We are loading the data set. We are initializing the k value. For getting the predicted class, we are going to iterate the total number of training data points, calculate the distance between the unlabeled data point to all the labeled data point. Once the distance are calculated, we have to sort the calculated distance in the ascending order, and we have to take the top k rows, because when k equal to 3, then we have to take the top 3, and out of the top 3, is of which class, majority falls into which class, that class is the predicted class, and it returns that predicted value. Now we will see a small example. So for the KNN classification algorithm, we are given a data set of patients with the health parameters of blood pressure and cholesterol. And this is the label. So disease or the class label is either yes or no, whether they have the disease or no. You are tasked with predicting if the new patient is likely to have the disease based on the health parameters. So how are we going to find? So the new patient's blood pressure value is 125 and the cholesterol level is 210. We have some five already analyzed patients' data with the labels telling if 120 is the blood pressure and cholesterol level is 200, the disease, it is not, they don't have a disease. Okay, their health parameters are normal. Otherwise, it is abnormal and it should be treated. So that is how the data set is. So for this data set, we have to calculate the first thing what we have to do. And now we are assuming k equal to k value as 3. So when k equal to 3, what are we going to do? So now the new data point for the new patient is blood pressure level is 125 and cholesterol level is 210. So when we take the data set, we have to calculate the distance. So we have to calculate the distance of this patient's BP and cholesterol with respect to the new patient's BP and the cholesterol. So 125 minus 120 the whole square plus square root of 210 minus 200 the whole square. So when we take this, we get a value of 125, which is equivalent to 11.8. So the same way for the next one, 125 minus 130 the whole square plus 210 minus 220 the whole square, which will again come up to 125 and 11.8. The same way for the next data point, it's 125 minus 110 the whole square and plus 210 minus 180 the whole square, which is having a value of 33.54. The same way, when you calculate the square root of 125, the new patient's value with the old patient value of the fourth patient value, 140, the whole square, less 210 minus 240, the whole square, we get around 33.54. And for the last patient, 125, the distance of the unlabeled data is 125 and 210. These are all labeled data. So 125 minus 115, the whole square, less 210 minus 190, the whole square. The value comes under to 22.36. So finding out the distance of these these 5 patients with respect to the new patient who's having a cholesterol level of 120, blood pressure level of 125 and cholesterol level of 210. After we found out the distance, we have to sort it. So when we are sorting, this comes first, this comes second, and here it is third. Then these two are fourth and fifth. So this is how we sorted it. And when k equal to 3, we have to take the three nearest neighbors. So we have to take 1, 2, and 3. These are the 3 neighbors to the patient's value, this new patient's value. So now we have taken these 3. And what are the class for these 3? The 3 classes are, one is no. For this, the disease class is S. And here, the disease class is no. So out of these 3 neighbors, what is the majority class that is available? The majority class is no. So now we are able to classify the new patient's data with assuming that they don't have a disease. So the new label is no, because majority out of the 3 neighbors, no is the majority value. So we are predicting, we are classifying this patient is not having a disease. So that is how we are classifying. So when we are classifying, we have to make sure that choosing K is one of the important tasks, and it is very critical, which will affect the algorithm of the performance of the algorithm. And the cross validation is typically used to choose the optimal K value. Then we'll keep on validating, make an optimal value for K. We have to do normalization because when features are of different scales are there, it is important to normalize the data before applying KNN. Few features will be in centimeters, height will be in kilograms. So to avoid skewed output, we have to make sure that it is being normalized. Then only when we take the distance measure, we'll get a proper normalized output. So normalization is very important for the features that whatever features we are going to take. And distance metrics can be any Manhattan or Euclidean. Based on the distance metrics, the performance of the algorithm will be modified. So This is with respect to the classification algorithm, and I'll show you the simple code for the same data that we have executed. You have to be working with your data set, but I have used the same data for you to show how this algorithm is working. You have to import the necessary files, and scikit-learn library, we have to import the test and training data, import the K-neighbor classifier. Standard scalar is to standardize the feature, normalize the feature, and to find out the performance metrics, whatever performance metrics we are going to find, we have to use that. So we are going to find out the accuracy, recall, precision, F1 score, ROC curve, whatever we have to find, we have to import those libraries necessary. So this is my sample data set. For the sample data set, we have to create the data frame, and in which we are taking blood pressure and the cholesterol level as the features, and its respective labels as the disease, which are no, S, no, S, and no. We are taking it as Y and X. Now we have to standardize these features, because for any KNN algorithm, we have to standardize the feature using standard scalar, which will help us to normalize our data. So standard scalar is used, and I'm giving my X value, my blood pressure, cholesterol value for the fit transform to standardize the features. Once the features are standardized, then I'm giving that standardized features for splitting and training. So here 80% data is used for testing, so training, and 20% data is used for testing. So we are giving the X scaled and the Y data. X is my cholesterol, and the X scaled has my standardized cholesterol and BP levels, and Y will have the labels, respective labels. So now 80% of data is training data, and 20% of the data is considered to be testing data. And as we are initializing K as K in KNN classifier for K, how many number of neighbors as K as 3. So N underscore neighbors is equal to 3. And once that is being done, we are going to train the model. So fit KNN.fit, where we give X train and Y train data. The training, 80% of training data is given. Once the 80% of training data is given, my model is trained. Now I'm going to predict. Actually, we have to predict from when I have a huge data set. I'll split my 80% of data as training data and 20% as my testing data, and that testing data has to be given for checking. Now I'm going to check with the new data that was asked in the question. So we are checking for the data, new patient 125 with cholesterol BP level as 125 and cholesterol level as 210. So we are converting this into a standardized feature for normalization, and then we are going to predict. So KNN.predict. We give this input for prediction, and the prediction will give the output. So we have used a formatted string conversion, where it is going to give the predicted value, and the predicted value is giving us no, and we also have calculated it as no. And this is a very small data set, so it becomes meaningless when I calculate the accuracy, because accuracy is 100%. So when you wanted to calculate for a data set, then we will be giving the KNN score with Y test, the predicted value that we are predicting, and the testing data set as such. And then we'll be able to find out how far the data that I have predicted is equivalent, or is it in line with the testing data that is being given from the data set. So that will give me the accuracy. For an example, 4 out of 5 test samples are correctly classified, then I have some 80% of accuracy that has been available. So with this, we will end with the